should be seeing my screen there. Let me know if that's not the case. But okay, so let me mention this on that thing first of all. 4.7, the video I created, I don't know, for some reason it didn't convert properly, so all you see is a black screen with my voice. I've since I went through the problems again and reposted videos of those problems, so you should be able to see those problems now working. Also, we are scheduled for a Chapter 4 test. That, at this point, so I'll get that out to you today or tomorrow. I haven't created it yet, but I'll get it out to you today or tomorrow. And because it's a take-home test, I'm not gonna put together a practice thing for you. I'm just gonna let you practice from your various sources. I'll just get you the test and we'll go. Remember, it's take-home. You'll submit it as a scanned document in Canvas, just like you do the homework. Okay. If you do have questions about that, feel free to ask. But it's going to be pretty low key. We'll just cover actually, yeah. Yeah. Okay. Anyway, with that said, just watch for that. I'll send it out to you. I'll send it out to you over the next day or two as soon as I get it created. So let's jump in with your questions.
So on 315, he listed the formula for the volume, and for some reason I keep getting weird answers for the maximum height.
Okay. Let me find it here. So 315 suitcase, the length, the width, and the height of the box must be less than or equal to 62. Assuming the height is fixed, show that the maximum volume is given by that equation. What height allows you to have the largest volume? All right, so to carry a suitcase, the length, the width, and the height of the box must be less than or equal to 62. So you should be seeing my screen. Length plus width plus height. We'll just say the maximum we can have is 62. Now, they're asking about the largest volume. So as I've said, when you do these problems, you look for that key because you look for the question that they want you to maximize or minimize, because that's going to tell you what equation you need to come up with. So we need an equation for the volume. All right. So the volume, of course, of a rectangular suitcase is length times width times height. But we can't have three variables. All right. We can only have two variables. So here's the deal. They're making an assumption, first of all, that the height is fixed. So what is the height? It's just h. All right, so that's really not a variable. H is just some constant. L and W are the only things that are going to get to change. So those are our only two variables. So let's suppose we decide to just write W in terms of L and convert everything to L's. Well, from this equation, W is going to equal 62 minus the constant height minus minus L. So in place of W here, I'm going to put what it equals. So L stays. We're fine with that as our variable. We may Yeah, I'm just going right there, so we'll see. 62 minus H minus L, and then that's our W, and then H. So the equation for the volume is 62 LH minus LH squared minus L squared H. Okay, so there's the equation for the volume dependent on L. Now, so that the maximum volume is this. So that's just the volume. So the maximum volume, well, so if we want to maximize this, we know what we got to do. We got to find the derivative, right? And remember, this. Let me be more precise. We're differentiating this with respect to L because H is just a constant. So H is just a constant. So when you differentiate with respect to L, you're going to get a 62H minus an H squared minus a 2LH. Because H gets treated as a constant through that. It's treated just like any other number would be treated. And so if I want to figure out when this is maximized, I need to figure out when that equals 0. And remember, we're solving for L, right? So let's just do it this way. 62H minus H squared equals 2LH. And we divide by 2H. And so we end up with 2H. We end up with L equals, what's this? 31 minus 1/2 H. 31 minus 1/2 H. Okay. So that's when we will get the maximum volume is at 31 minus 1/2 H. All right. So I've talked a little bit. Well, let me just finish. So what would the maximum volume be? Well, it's what we get when we use this as L. So let me put that. So our volume again is right here. So for L, if I want to maximize it, I plug that value in for L. So it's going to be 62 times 31 minus 1/2 H times H minus 31 minus 1/2 H times H squared minus 31 minus 1/2 H squared times H. So I just plug that in for all of these L's, right? And we could do a little algebra on it right here. Now, do I want to do some algebra on it? It's like a lot of. Okay, let me stop there for a second and see if we've answered your question or see if we've given you some direction.
Yeah, I was treating H like a variable. That's what it was.
Okay, yeah. So we don't want to do that. Just looking at something here. Yeah, 62 LH minus L H squared. So if we work this out, so for instance, I think I can factor out a 31 minus 1/2 H and an H from everything. And that's going to leave me with 2 minus H minus 31 minus 1/2 H. Okay.
So what's the volume equation that they give us used for?
Well, yeah, so they don't give us the volume. They're saying that is the maximum volume. Okay. They're saying that's the maximum volume. So that's what. So if we that's what we're trying to find here. We found that we get the maximum volume when this is the length. All right. Actually, let's make our life a little easier. I think I'm making this a little harder. Yeah, let's try this. So I'm going to back this off. All this work that we've done up to this point is in order to find out what length we need in order to get the maximum volume. So rather than do this, I'm not saying that's wrong, but rather than do that, I'm going to just do it this way. I'm going to say, okay, we get the maximum volume when h equals h, because that's constant, right? Let's do this like this. When h equals h, so we're max volume when h equals h, when L equals 31 minus 1/2 h, and when W, that means W is equal to, look right here, right? W is equal to 62 minus h minus 31 minus 1/2 h. Okay. If we look at that, 62 minus h, that becomes a 31, because 62 minus 31, and then minus h plus half h is minus 1/2 h. So there, okay, this is much nicer. When the width is this. So we get maximum volume when these are the three values. Well, what is the maximum volume? Well, use those three values. H times 31 minus 1/2 h times 31 minus 1/2 h, right? Height times width times length. And that's what they give us. So that's going to be our maximum volume. That's what the problem says. What is the maximum volume? If I continue this, I should get this. Okay. I could have dropped something in here somewhere. Yeah, no, I don't. Yeah. So for instance, this is not a 2. This is a 61. I'm not sure what it's here. Or 62. 62 minus h minus. Yeah. So that's going to be the same thing. So that's what the volume is. The maximum volume is what they give us, and we found it there. We also found it there. We were just half a step away. Does that help? Give me some pluses if that makes sense. It's a little complicated just because, yeah, you're like, where does that be? I mean, it's a little hard because it's easier when h is, if it would be easier if h is just a number. Bam, here's the number. But no, we got to play with h and leave it as an h through all our calculations. So, okay, good question. What other questions do you have?
So what about the second half of that where it asks us to solve for h?
Oh,
We want the max height of h.
What height around? Okay. So yeah, so that's kind of an interesting question. So let's see. Yeah, so let's just see. So we don't typically do it this way, but we just found that the volume is maximized when we have this as our height. like that. Okay, so our heights can be anywhere from 0. They could go all the way up to 62. That makes no sense, right? It makes no sense to have a height of 0, first of all. But it makes no sense to have a height of 62 either, because then you have no width or length to play with. But those are your extreme cases. So somewhere between 0 and 62, you have a maximum, a height value that maximizes this right here. Okay, that makes this as big as possible. So if you want to find out when that is, you just take the derivative of it, right? And so you're doing it again, but now you're finding the maximum height. So you're just going to take the derivative, find the critical points, and go from there. So this is a product rule. So the derivative of h times 31 minus 1/2 h squared plus the derivative of 31 minus 1/2 h squared times h. So the derivative of h is 1. And then the derivative of this in the square brackets is 2 times 31 minus 1/2 h to the 1 times negative 1/2. And then times h. So we want to set that equal to 0 and solve for h. Just looking to see if there's a, yeah, so if I factor the 31 minus 1/2 h out of both, then I'm left with 31 minus 1/2 h plus 2 times negative 1/2 h. Yeah, this is going to be easier. Or just 31 minus 1/2 h times 31 minus h, I believe, because that's a minus 1/2 h, and then it'll be a minus another 1/2 h, so minus h. And so I just want to figure out when that equals 0. Well, it's already factored, so when h equals 62, that's what this, well, so what I do is I set each factor equal to 0. Right? That one equal to 0, and that one equal to 0. And this one will give us h equals 62, and this one will give us h equals 31. Well, this makes no sense, this first one, because remember, the sum of your 3 dimensions has to be at most 62. So if your height is all 62, then that means your length and your width are both 0. And so, you got this weird, one-dimensional suitcase. Doesn't really work. So we throw that one out, but what we learn here is 31 is the answer. So we need to make our suitcase have a height of 31, and then that will help us maximize the volume. Okay? All right. Any other questions on that? Or on other things? We can keep going. So yeah, go ahead.
Oh, I was going to go on to the next question, but if you're still talking about this one, I can wait.
No, I'll just say this, and then you can go on. This problem is really unusual in that you've got, you're dealing with this constant h, so you're floating this variable through the whole process, and then you have to redo the maximization or the optimization process again a second time to figure out what the maximum is. We don't do that very often. So anyway, do your best on that one. What's your question?
So on 4.8, 357, it uses k. Is that just a constant?
Sorry, 4.8. So 357. So yes, it's just a constant. In other words, it can be anything.
Okay, so like when we use the product rule, or not product, power rule to find the derivative of g of x, would we find, so like for the first derivative I get k of x raised to the k minus 1. Would the next one be k times k minus 1 times x raised to the k minus 2?
Yes, exactly. Now, yeah, you're exactly right. Now, you got to work different cases. So you got to say, okay, if k is 0, right? Then you're just looking at the limit as x goes to infinity of e to the x, because x to the 0 is 1, right? So if k is 0, boom, you've got just that one limit, okay? If k is positive, then you do what you're talking about, okay? If k is negative, then you can move it up to the top and it becomes x to the k times e to the x. And then L'Hopital's doesn't apply, all right? So you've got your three cases to look at. K equals 0, k is positive, or k is 0. L'Hopital's will only apply when k is positive, and then you do what you're talking about. If k is negative or 0, then actually the limit becomes trivial, because you don't need L'Hopital's to evaluate it.
So to answer this one, will we put 3 answers, or how would we define that?
Yeah, so you're going to have 3 answers, one for each of those 3 different cases. So do it once. So for instance, let's do the weird one, right? If k is negative, so let's just imagine. So just so you guys know what we're talking about, we're doing the limit as x goes to infinity of e to the x over x to the k. And let's suppose we're looking at the case where k is less than 0, right? So that means it's negative, right? So that means what I can actually do is I can actually rewrite it as x to the k e to the x, right? Because if k is negative, then I can move it up to the top of the fraction, and now it's a positive. X to the k equals k to the x, or e to the x. All right? And now I want to evaluate the limit. So I can imagine, although I'm doing it for all values of k, I can imagine, oh, well, this could be a 2, or it could be a 3 or a 5 or a 7 or whatever, right? Or it could be 1/2, whatever. If I try to evaluate this limit, I just imagine, I know this thing is going to infinity. Okay? I know that's going to infinity. What's this going to go to? Well, it's going to go to infinity as well, right? Because it's going to be x squared, and x is going to infinity. So basically, you have infinity times infinity. That's easy. That's not an indeterminate case. That's infinity. Okay? And that's going to be the case for all k's whenever k is less than 0. You'll end up with some x to a power, which goes to infinity as x goes to infinity, times e to the x, which goes to infinity as x goes to infinity. Okay? For k equals 1, or k equals 0, it's even simpler because you just end up with 1, e to the x over 1. But for k is greater than 0, then you do what you're talking about, and you have to keep applying L'Hopital's rule until you can evaluate the limit, right? Because each time you apply the L'Hopital's rule, you end up with infinity over infinity. But eventually, you're going to get down to just e to the x over k times k minus 1 times k minus 2 times k minus 3, all of times k, which is just a number, right? So it'll be e to the x over some number, and then you can evaluate it. Does that help?
I don't think so. So you're saying it's not possible to, well, I guess it's possible, but we can just picture if k is greater than 0, and it'll keep getting smaller, so eventually there won't be an exponent anymore, so it would just be infinity over a constant, which is just equal infinity.
Yeah, so just imagine, right? So what you can do is you can just say, let's suppose it was 4, right? And so that's infinity over infinity, right? As the limit as x goes to infinity. So we apply L'Hopital's, which means take the derivative. Well, you take the derivative, you're going to get e to the x times 4x cubed. Try to take the limit again. Oh, that's infinity over infinity. So apply L'Hopital's. Take the derivative, e to the x over 12x squared. Still infinity over infinity. Apply L'Hopital's. E to the x over 24x. Still infinity over infinity. Apply L'Hopital's again. E to the x over 24. Oh, look. Now it's infinity over 24, which of course is infinity, right? So eventually, for these positive values, you're going to get down to e to the x over some constant. And that limit you can evaluate, because it'll be infinity over some number. Does that work?
Yeah, that's great. Thank you.
Okay. What else can I help you guys with?
If there's no one else, I also had a question on 375, where the limit as x approaches 0 of sine of x minus tan of x over x cubed equals like -1/2, but I got -1/3, I believe.
All right, let me catch up to you here in a second. Give me one moment. Okay, let's see. Okay, so tell me where we're at again, Xander?
So question 375. Do you need this equation or just?
I've got it right here. Limit.
Okay.
Okay, so there's what we're dealing with. Now, what was your question?
I got the answer of -1/3, where the book got -1/2.
The book got -1/2.
Mm-hmm.
Okay, let's take a look at this. So we're just doing this right here. All right, so if we try to evaluate this limit, we imagine x going to 0, and we notice that, of course, sine goes to 0, and tangent goes to 0, so the top is going to 0. And then, of course, x cubed is also going to 0, so it's 0 over 0, so it's an indeterminate form, so we can use L'Hopital's. So L'Hopital says, you can just take the derivative of the top, derivative of sine is cosine, and the derivative of tangent is secant squared x, and then the derivative of 3x, or x cubed, is 3x squared. Now we try to evaluate it, right, by plugging a 0 in, and we notice, okay, this one goes to 0, this one goes to 1, this goes to, well, 1 as well, right? So 1 minus 1, that goes to 0, and then the bottom goes to 0 again, so we apply L'Hopital's again. Derivative of cosine is negative sine. Now we got to take the derivative of secant squared. So minus, so we'll have 2 secant to the first power, and the derivative of secant is secant tangent. It's a chain rule, and then 6x. All right, let's Throw in a 0 again, we get 0. We get 1 there, we get 1 there, we get 0 there. So 0 minus 0, and again 0 on the bottom. So L'Hopital's again. Let's make our life just a little easier, of course, noticing that this is secant squared x tangent x, right? So L'Hopital says we need to take the derivative again. And thank goodness the bottom is now just 6. So we know we're at an end in sight. So the derivative of negative sine is negative cosine of x. Minus, now we'll put this in parentheses, we're going to take the derivative of 2 let's do it this way. We're going to make our life easier. We'll leave the 2 outside. And we'll just take the derivative of secant squared tangent. Okay? So, the derivative of secant squared is 2 secant tangent times tangent. Okay? Plus, the derivative of tangent is secant squared x times our other secant. Alright, so that should be our derivative. Alright, we're not going to simplify because we know we're just plugging in a 0. So this would be a minus 1. This will be a 1 and a 1 and a 0 and a 0. So that whole term, that term right there disappears. And then this becomes 1 squared and a 1. Alright. So it looks like this becomes minus 1 minus 2 times 1 over 6. So negative 1/6. Sorry, negative 3/6. Or negative 1. Sorry. Yeah.
So secant squared x for 0 equals 2?
Secant is 1. Secant is 1, so secant squared is 1 squared, right? You're wondering where I got this to right here?
Yeah. Oh, is that from the front?
That's from way back here.
Alright, okay.
When we take the derivative of that secant squared for the first time.
Oh, I see. Okay, so what I did was I got negative 4 somehow, and then I also applied that to only half the function, not only the first part, but the second part. So that's where I got that. Okay, thank you.
Yeah. So, some tricky differentiation there. But that's a good question. Okay. What else can we talk about? What other questions do you have?
If there's no one else, I was curious about using antiderivatives with a quotient. So there's x of 1/3 over x of 2/3, 4.10.
Yeah.
And I don't really know how to deal with that or with products.
Okay. Yeah, so you can't. The short answer is you can't. In fact, because the only antiderivative you can take, the only rule you have for antiderivatives is that you know right now is the power rule. Other than just taking antiderivatives of cosine and sine, right, which are you've just memorized their antiderivatives, right? So this brings up a really good point of how do we deal with this. And it's going to be a little like when we were finding derivatives, when we only had the power rule, right? So we have to convert things so the power rule applies, All right, so do you have an example that you're specifically looking at?
Yes, the first one is 479, where we have x of 1/3 over x of 2/3, finding the antiderivative of that.
Yeah, so you'll recognize this idea. X of 1/3 over x of 2/3. We're going to use our little notation, right? Find the antiderivative, okay? But here's the deal. You can't use that, the power rule, with a quotient, right? Because that's what you're seeing there. But look what we can do. We can use simple algebra to rewrite that as, look, I can subtract the exponents. 1/3 minus 2/3 is a minus 1/3. And so really, that's what I'm dealing with, right? So I simplify it. Now the power rule can apply. So it's going to be x to the increase the power by 1, x to the 2/3 over 2/3 plus c, or better, 3/2 x to the 2/3 plus c. So this is just algebra, right? That's just rules of exponents. No calculus there. But doing that allows us now to apply the power rule. So yeah, you've got to convert everything into something that you've used before. And later we'll talk about how to, find the antiderivative of way more complicated things.
That does make a lot of sense. So thank you.
Okay. Probably have time for another question if you guys have it. So we're following a schedule, right? And I'm trying to continue to produce content here for these things. So do your best to keep up. We don't want to get too far behind, right? So, like, for instance, today we wanted to be talking, or you should be looking at some stuff from 5.2 when I get that posted. But you're doing a lot of work on your own, but then send me messages in Canvas if you have questions. So if you don't want to wait till these Monday and Wednesday sessions, send me messages in Canvas. What else can we talk about in this last few minutes we've got?
I had a similar question on 497, where we have x to the 3rd in the quotient instead of underneath the polynomial.
Yeah, so again, you're going to do some algebra first, right? You're going to play this game. And see, this is the same thing that happened. I gave you this kind of problem, said find the derivative way back in the day, and before we had the quotient rule. And what you had to do is you had to say, oh, I can break it up like this, 14x cubed over x cubed, plus 2x over x cubed, plus 1 over x cubed. And now each of those can be simplified and fit the power rule. So if I were taking the derivative, that's what I would do. If I'm taking the antiderivative, this is what I'd do as well. And then I just use the power rule.
Okay, that makes sense. Thank you.
Okay. Now, let me just talk. You guys feel free to interrupt me. I'll talk a little bit while we've got this time, but feel free to interrupt me and ask questions. When you get to 4 or 5.1, we're actually returning to a topic that we actually explored early in this section, or early in this semester, and that is finding the area under a curve. And the goal was, remember, I'll just give you this. We have a curve. I want to find the area under the curve between those 2 points. And so the game we played was we, divided this up into however many intervals, and then we used the right hand or left hand to create rectangles. We found the area of each of those rectangles, added them up, and that gave us an approximation to the area that we wanted. Well, we're doing that in 5.10. We're returning to that idea. If I want a better approximation, then I would use more rectangles, right? I would cut each of these rectangles in half and then use the right hand rule. in 5.1, you're going to see the same idea. We're going to put a lot more notation to it because we need the notation to actually find these areas, right? We're going to use limits to do this. We're going to basically, what I want to do is I want to make the number of rectangles. If I truly want that area, I want the number of those rectangles to go to infinity. So I'm going to set up things so that I find a limit as x goes to infinity, or as n goes to infinity, where n is the number of rectangles, right? And it's really cool. We end up with the exact area using limits. So that's what you're going to see the beginning of in 5.1 and in 5.2. Right. Any last questions before we call it a day?
How far does
your question broke up, so ask that again, would you?
yeah. How far does 5.1 go? Does it go just to Riemann or the Riemann sums?
5.1 just repeats this process that we did at the beginning of the semester with some more notation, relying a little bit more on notation, plus it introduces the idea of summation notation. And you should see videos for all of that in the online module. Yeah, we'll actually start evaluating these limits and finding these areas using limits in 5.2. Okay. All right, guys, we're to the end. Let me just, again, we meet a couple times and these are hopefully productive, but feel free to send me questions in Canvas in between time, right? Because I don't want you to get so far behind waiting for these twice weekly meetings that things start piling up. So feel free to send me other questions. That'll at least guide me as to what kind of videos to create. I can quickly create out a video and get it posted for you. But I just don't want you to feel like, oh, I can only ask questions, during these times. So anyway, have a great weekend. Be safe out there, and stay home, right? And are you still on campus, Ryan?
Yes, I am.
Okay. Things pretty quiet on campus?
Yeah, there's not a whole lot going on here.
Okay. All right. Okay. You guys let me know if you have questions. We'll see you next time.